week of sessions at the IITians Hub last week, and got some new and interesting things to learn and think about, right? So this week was also going to be similar to last week in terms of the number of lectures and amount of workload, etc. But obviously, as we get into the second lecture of each and every topic, you will see that the nature of the subject is going to get a little bit more technical. So level of difficulty of assignment, etc. will increase slightly. But just take it one step at a time, right? And take it as a new learning challenge and enjoy it. Okay, there is no super hurry right now, and there is no huge amount of pressure on you for anything. Okay, but at the same time, you have to start getting into that process this week onwards, where you have a proper working routine. Okay, if you haven't started already last week, then please start with these basic things this week, that you have a proper personal timetable, right? You have a designated time for waking up in the morning according to your lecture schedule. You maybe have a bit of time for relaxation or exercise before your first lecture starts. Then during the day, according to your lecture schedule, you have enough number of time slots that you have put for self-study, right? And that self-study should first of all include the revision of the content of any lectures that you have had. Okay, so like I said, that you can scribble the basic notes of the class as you're going through the class. So the first task after the class should be to go through those notes and revise and recall all the things that were done. During that process, you can also have you can also sort of fare your own notes. Okay. Yes, Nishya, to answer your question, there will be physics and chemistry doubt sessions also coming up very soon. Okay, but you can always send the doubts that you have during the week, regardless of doubt sessions or not. You can always send the doubts to your teachers. Coming to the subject of doubts, I think most of you have joined the Discord platform. Okay, you must have seen there was a Discord invitation sent, I think, by Tausif sir last week. If you haven't, then please join the Discord platform. You will see it's a very organized platform in which there are different there are different chat rooms, sections, etc. that you can join. So in that, you can post your doubts also in one place, separate place for physics, separate place for chemistry. You can start doing that from this week onwards. There will also be channels in which specifically the physics videos or the calculus videos, the vectors videos, the structure of atom videos and notes, etc. will separately be posted. So that way, compared to a WhatsApp group, it is much more organized. It's later at a later time when you want to go through all those things, they will all be at one place. They'll be easier to navigate through. Okay, so you can also start exploring the Discord platform. I'm sure most of you are already familiar with it, being gamers and all. But if you're not, then just join through the link and catch on. It's pretty easy. It's like any other social media platform, more or less. Okay, with certain conveniences for sharing files and things like that. Okay. Yeah, I will be discussing part of the worksheet today, Abhinav, but I have also sent a sheet with the answers and some hints. And I think after today's lecture, once you go through those answers and hints, it will be pretty easy to understand most of the questions, okay, in the worksheet. Okay, so don't worry if you could not complete the worksheet or could not get the answers in a couple of the questions. Okay, it's a learning process, okay, and the first lecture was anyway general, so we haven't learned any specific formula, etc. in calculus yet. So not really expected to be able to solve everything yet. But today's lecture, as I said, will become more technical. Okay, so let's go ahead. Just before we start, let me reiterate, like, this is the right time to start making a proper study schedule and routine for yourself. Make sure that you're making a personal timetable in which you have fixed study hours. You have some amount of fixed time for your hobbies and relaxation. Try to keep hobbies such that it is away from a lot of screen time. Okay, whether it is video games or social media or whatever, try to limit the time that you're spending on a screen, a tablet screen or a laptop screen or whatever, because believe me, it will create a certain amount of strain on your eyes, especially with the extended lectures, etc. that you will be going through. So So, and as far as your studies is concerned, try to do more and more pen work. Okay, so when you are even revising a lecture, for example, keep a notebook, even if it's a rough notebook beside you, so you scribble the basic points. Every time there's a numerical problem that you're revising, try to do the steps yourself on pen and paper. The more pen work you do, you'll see the more organized your thinking becomes, and the more you're able to recall what you have to do in problem solving when it comes to solving an assignment or solving a fresh problem by yourself. Okay, so these are some of the basic things. We will discuss more about these things as we go along. So let me come to the subject. Yes, Jairaj, to answer your question, Jairaj has asked in the chat message that you have to use the you have used differentiation to solve the worksheet questions. Yeah, you can use differentiation. There's no problem. But the whole idea was that the first worksheet was just to do with rate of change. So you could have just used the basic concept of rate of change without getting into the technique of differentiation into that. Okay, differentiation is a process in maths that will help us calculate rate of change in a very easy and systematic manner in future. Okay, as we will start learning today. But the first worksheet, the problems were such that you didn't really need to use differentiation. If you use differentiation, there's no problem with that at all. Okay, so that is why you will see the hints and answer key that I've sent, especially the hints. I have not used any technique of differentiation anywhere in solving the questions. I've just sent it a few minutes back, so you might not have gone through it. Take your time to go through it later today, but you will see that I have not used differentiation at all. I've just used the concept of rate of change. Okay? There's the idea of slope, okay, of secant line or slope of tangent line, okay, that kind of concept. Okay, right. So let's begin today's session content wise. Okay, so we will start with a bit of quick recap of what we learned in the last lecture. So this is session number 2 for our basic calculus. So first of all, one of the important things that we discussed in the last lecture was the concept of a function. Okay, let's go over that again, because now we will talk about rate of change in a general context. We will not talk about rate of change only in context of average speed and instantaneous speed, like we had started with. Okay, for example, I've given you a problem in the worksheet which has to do with volume of liquid in a container and the rate of change of volume, and accordingly the height of liquid that is there in the container and the rate of change of height, etc. So it can represent, we might want to calculate rate of change for any physical parameter. So that's why we have to deal with functions in general and not specifically only with the kinematics parameters. Okay, so whatever applies to functions can now apply to the relationship between any physical parameters like displacement and time, or velocity and time, or volume of liquid in the container and time, okay, or position versus let's say kinetic energy, or any such thing in the future. Okay, so functions, let's understand what we learned about functions last time. So what we saw, the definition of a function as was that it is a simple relationship between two variables. Okay, a function is a relation or a map between two variables, let's say one variable y and the other variable x, where the function defines a relationship between the two variables. Okay, it can be any other symbol also. I can say s is f of t. So this would just say that whatever the variable s is, it can be displacement, it can be distance, whatever, is a function of the other variable t. Now typically t would represent time, so I'm assuming here that s is either displacement or distance as a function of time. So like that, in general, I will say over here that y is a function of x. So this above is the symbolic notation for that. Okay, whatever I'm saying over here below, I'm just saying that in symbol above, that y is equal to fx. Okay, and again, f, just using the symbol f is a matter of tradition. We can use any other symbol also, any other letter also we can use. Okay, so you don't have to use just the symbol f. We can say that y is g of x, or we can say y is f1 of x. And all these basically mean they're just using some arbitrary symbol. So standard symbol for the function is small f, like this. Okay, now here the hidden meaning, the understood hidden meaning is that x is what type of variable? It is an independent variable. That means I can select the value of x without looking at the value of y. There is no It's selected independently. But y then becomes what we call the dependent variable. That means the value of y is now dependent on the value of x. The moment I've selected some value of x, I get a corresponding value of y, which is according to this rule. Okay. And of course, there was one important limitation here for us to understand, that any value of x, any particular value of x must map to, or must give, you can say, okay, a unique value. It must give a unique value for y. So if I take a particular value of x, it should not point to more than one value of y. It should point to a unique and particular value of y alone. So that is a limitation that we have in the definition of function. That's all we need to understand about functions. Okay. So we can also visualize a function as, it is some kind of rule or relationship. Okay. Where if we input the variable x, the corresponding output that we get will be the variable y. Okay. So for example, if that function happens to be, let's say, 2x plus 3. So that means when we input x as, let's say, 0, we get the output y as 3. If we input x as, let's say, minus 1, we get the value of y as you can see, plus 1. If we input x as minus 2, for example, we get the value of y as, how much is it now? Minus 1. Okay. So on and so forth. Okay. So different types of values. If we input x as 1 or plus 1, we can get the value of y as 5. If we input x as 2, we can get the value of y as 7. Okay. Another example would be, let's say, the function is the square root function. Okay. So here we understand, of course, that x can only be between 0 and infinity. Okay. So we say that x is non-negative, because that is the nature of the mathematical rule of square root. We cannot define square root of a negative number. At least it doesn't come in the domain of real numbers. Okay. Whereas here x could be anything. That is just an additional thing to understand, that it could be anything between minus and plus infinity. Okay. So anyway, so here if we input x equal to 0, we can see that corresponding value of y is 0. If we put x as 1, we can see the value of y is 1. If we put x as 2, we can see the value of y is approximately 1.414, whatever. X as 3, y is approximately 1.73. X as 4, the value of y is 2, and so on and so forth. So these are all examples. So you can just visualize a function as a sort of a machinery, okay, that changes one variable into another variable according to some kind of rule. So if the rule happens to be this, then these are the set of outputs that we get for this corresponding set of inputs. If the rule happens to be this, then this is the output that we get for the corresponding inputs which are like this. So this is one simple way to visualize a function. Okay. Another way to visualize a function we saw is through a graph.
So imaginary numbers can also be a part of function 1, right?
Yeah, I mean, in the complete universal set of functions, you can say yes, we can define functions for imaginary numbers also. Okay, so they can be defined such that x and y are not only real numbers, but they come in the set of what we call complex numbers. That is, it has a real part and an imaginary part. But here for our physics partner, we will not get into, in fact, even in maths, okay, when you do functions later in maths, as part of the calculus syllabus of maths, you will be dealing with real functions only. Okay, complex number functions go into a different category. Okay, beta, so hope the point is clear.
Yes, sir.
Okay. Yes, sir. Okay. So at the moment, you just think of the functions as the in that the variables have to be real numbers. Okay. Yeah. So graph of a function is just a visual way of representing the same information, as you know. So the only thing we have to remember about the graph is that the the convention that we take is that the vertical axis always represents which variable? The dependent variable, and the horizontal axis always represents the independent variable. So for example, if we are representing y as a function of x, this is how y should be, and this is how x should be. If we are representing s as a function of t, then s should be on the vertical axis, t should be on the horizontal axis. Okay. And then the function, the so-called graph of the function will just be the curve that represents all such points that satisfy any point on the curve, let's say p, which has some y coordinate, let's say y prime, and some x coordinate, let's say x prime. So any point p on the graph or the curve that represents this function must satisfy the function itself. That means if I have
but this convention can also be changed, right? If we can reverse that independent as y on y-axis and dependent on x-axis, because many times in questions they reverse the quantities.
See, yeah, so I will come back to that. If they reverse that, then to make the proper graph of the function, we have to actually convert it back to this. You understanding the point? Because otherwise, a lot of the interpretation of the function will go wrong. Okay, I'll give you a simple example how the interpretation of the function will go wrong. Okay, for example, if you are calculating the rate of change of distance with respect to time as the speed, then when you take distance on the y-axis and x on and time on the x-axis, then what will the slope of the graph represent? It will represent, if it's a tangent line, it will represent instantaneous speed. If it is a secant line, it will represent average speed. Right? This is clear?
Yes, sir.
But if I take time on this axis and s on this axis and then plot the graph, whatever it will be, now what will the slope represent? Will it represent average speed? No, no.
No, sir. Sir, it will
represent inverse of
it will.
Yes, sir.
I'll have to take 1 upon the slope. Okay, so the interpretation becomes reverse. So that is why we have to follow a strict protocol. And in any case, the protocol for drawing a function is the graph of a function is always whatever is your independent variable that should be taken on the horizontal axis. And whatever is your dependent variable, because when we talk about rate of change of function, it is always delta y by delta x, not delta x by delta y, where it's understood that y is the dependent variable and x is the independent variable. So for that reason, because rate of change is change in the dependent divided by change in the independent. Okay, so that's why it has always got to be in such a way that y-axis or the vertical axis is your dependent variable and your horizontal axis is the independent variable. Okay. So this is again a convention that you should remember. This is the independent variable.
So I had a question that the graph we draw that t was on y-axis and s was on x-axis. So how do we exactly convert it into conventional type?
Oh, that's easy. That we will see with practice, beta. That will happen. Don't worry. That is just a matter of bit of experience in with graphs and plotting graphs, etc. But the one simple way, see, you can always convert a graph into ordered pairs. Like if the graph is actually drawn on graph paper, you can convert a set of points on the graph into a set of ordered pairs. Ye kar sakte hain?
Yes, sir.
Okay, and then just write the ordered pairs in reverse order. So make a new graph where you plot the ordered pairs in reverse order, where you take x as the vertical axis and y as the horizontal axis.
Yeah. Okay, sir. I got it.
So when you do that, you will see that it sort of becomes a mirror image about this 45-degree line. Yes, Nishchay, you have a question, beta?
So it will be symmetrical, right? About that x-axis.
In fact, not only it will be symmetrical, it will become a mirror image about the line y is equal to x. Okay, I'm just getting a little ahead of myself over here. I'll come back to this point. Okay, so let's finish writing down this point. So every point on the graph must satisfy the equation. So any point which has a particular coordinate, let's say x prime comma y prime, it should satisfy the equation that y prime is given by this formula with respect to x. Okay, so there is something called inverse functions that we will study about in maths later, not necessarily in physics. So what happens is that if we have a graph of y versus x, which is let's say like this, Okay. Then the corresponding graph of x versus y. And the same thing if I want to also show x versus y, that will become like this, that I'll have to first draw the line y is equal to x. Okay, this line. So this one is representing y as a function of x. Okay. Now the reverse of that will be represented by this kind of thing. Okay. So it will become a mirror image of the first graph with respect to the line y is equal to x. Now, why that becomes is little bit complicated if you are not familiar with this yet. So don't worry about this right now. Okay, you will see this later, that if y is some kind of function of x, that means x can be defined as the inverse function of y. This is not to the power -1. Okay, this is, I mean, this is not 1 upon fi. This is called the inverse function. So for example, if y is equal to x square, then x is equal to square root of y. Okay, so if you look at the graph of y is equal to x square in the positive domain only, it looks like this. But if you look at the graph of, now I've just interchanged the names, so don't worry. Now x is the dependent variable, y is the independent variable. So this graph actually looks like this. Okay, so you will see that it is actually a mirror image about the line y equal to x for the original graph of y is equal to x square. Okay. So this is the inverse function of this. Yes, Nishchay, you have a question, beta?
Sir, in the first case, y can be negative, but in the second case, like x will be always having a positive value, right? Because in the second case, we can take y negative also. X negative also.
Yeah, it's reverse actually. No? First case, whatever value of x we take, y is positive. That means when we look at the inverse function, over here, y is the dependent variable now. Okay, so that dependent variable should be non-negative.
So it's a restriction, right? We cannot obtain.
There is a restriction. Okay, there is a restriction. Okay, so anyway, let's come back to the point of rate of change of function. Okay, so you need not worry about inverse functions right now. It will be something important for you in maths later. Okay, here we are more concerned with, given a function, how to find the rate of change. Okay, so before that, let us look at the concept of rate of change itself. Okay, so Nisha, I hope that point is clear to you.
Yes, sir.
Okay. Why it's becoming like that, that in the second function y became the independent variable, so it had to have non-negative values. It can have only 0 or positive values, because in the first function, that's what you're getting now. For whatever value of x you substitute, the value of y cannot become negative. So accordingly, when you take inverse of that function and y becomes your dependent variable, then it cannot have a negative value in the real number domain.
You only look at the positive part of the axis, right?
Yes.
To get that symmetry.
Correct. Okay. Okay, so next thing, this is where the calculus part starts for us. We looked at rate of change of a function. So when we talk about rate of change for any function, there are two types of rate of change, as you saw. There is average rate of change. So for a function y is equal to fx, the average rate of change as a quantity is just defined as delta y by delta x, which you can further write as some value of y2 minus y1 upon x2 minus x1. Okay. So this is the rate of change for the interval x equal to x1 to x equal to x2. Okay. So further we can write this as f of x2 minus f of x1 divided by x2 minus x1. So as we had seen last time, that average rate of change is always defined for an interval. It is not defined for a particular instant or for a particular value of x. It is defined for an interval. This is the important takeaway here. Okay. So let's just do a quick example. So suppose I have this function y is equal to sine square x minus sine x. Okay. Now I ask you that find delta y by delta x from x equal to 0 to 30 degrees. Okay. Can you quickly find the value for me? What should be delta y by delta x for this interval x equal to 0 to 30 degrees?
Sir, it's very weird value. I think I'm getting -1 by 120.
Okay, very nice. That's correct actually. Okay. But that is provided we are taking x in degrees, and that's fine because I've given you x in degrees. Do you know about radians, like as a unit of angle?
Yes, sir.
Yes, sir.
Yes,
So
sir.
if you had taken x in radians, we would have got a different value. Yes, Prabhas, your answer is correct. The second one. Aparna, your answer is correct. Very good. So अगर हमने x को radians में लिया होता, we would have taken x from 0 to pi by 6, ना? So then we would have got a different answer. Okay. So let's understand here anyway what we'll get. Okay. So it's very simple. Y as a function of x. That function is now defined as what? It is defined as sine square x minus sine x. Okay. And I want to find delta y by delta x from x1 equal to 0 to x2 equal to 30 degrees. Okay. So correspondingly, delta y by delta x will be y2 minus y1 upon x2 minus x1, where y2 will be f of x2. So in this case, f of 30 degrees. So that will become sine square 30 minus sine 30. Okay. So that will become 1 by 2 square minus half. So that's minus 1 by 4, correct? And similarly, y1 will be f of x1, that is f of 0, that is sine square 0 minus sine 0, which is 0 minus 0, or sorry, not 1, but properly defined as 0. Okay. So then you can see, coming back here, delta y by delta x from x equal to 0 to 30 degrees, that's just becoming minus 1 by 4 minus 0 divided by 30 degrees minus 0. Okay. So it's becoming minus 1 by 120. Okay, now in this, there is just one thing. This now has a unit. This is per degree. Okay, because y is just a number here. It is unitless. Okay. X is also actually unitless, but it is expressed in degrees. So the unit of the rate of change becomes whatever the unit of y is divided by whatever the unit of x is. So here y is unitless, but x is in degrees. So we will say it is minus 1 by 120 degrees. Sorry, per degree. Okay. Now same thing, suppose I had expressed x in radians, then I would have got a different value also, and the degree would have been per radian. Okay. So first of all, please go through these steps carefully. Anybody has any doubt, please. Okay. please bring it to my attention immediately. Yes, Abhinav, your answer is also correct. Very good. Nitish, you understood? Good. Okay. If anybody has a doubt in, yeah, Nishchay, you have a question, beta?
Sir, but how can we express a quantity that has no unit and we are linking it to the one that has some unit with it, like x is in degrees and y is unitless?
You बिल्कुल कर सकते हैं ना. देखो अगर अगर मेरे पास अगर ऐसा होता ना that displacement is a function of time. So for example here, suppose we had this equation that s is equal to 5t square. Okay, now suppose time is in seconds and displacement is in meters. That means what kind of quantity this 5 is? Can you tell me?
Constant.
Yeah, but what type of constant? Is it a numerical constant or is it a physical constant?
Numerical.
It's a physical constant, no? Because it would have some unit.
अच्छा, yes sir.
है ना बेटा? वो 5 का unit क्या हो जाता है? It would be meters per second square.
Yes sir.
है ना? So you can understand now how this function is converting a quantity which is in seconds time into something which is in meters, because it's linking it with other physical constants. But for example, when I use the relation that area is equal to pi r square. Now in this r is in meters, let's say, so area will be in meter square, or if it's in centimeter. So यहाँ पे pi कैसा constant है? It is a dimensionless constant. So it's what we call a numerical constant. It's a pure number. है ना?
Yes sir.
Whereas in this equation, the 5 that I've taken, that is actually a physical constant. It has the same unit as acceleration. So here, when I express delta s by delta t, it will be in what unit? It will be in the unit of s, which is in meters, divided by the unit of time, which will be in seconds. Okay. But here, for example, if I express delta a by delta r, now e will be in meters square, r will be in meters. So the unit of this rate of change will be what? It will be in meters, in fact.
Sure.
You can understood this point, but okay.
Yes.
So yeah, so especially later when we look at the application of functions in the domain of physics, okay, where obviously the variables are not pure numbers, they are physical quantities, then the business of units will become important. So the rate of change of a function will have the unit of the the unit of the dependent variable y divided by the unit of the independent variable x. Okay.
Sir, but
yeah,
here, sir, then can you show in this degree example how this is exactly turning into unitless, like how y is turning into unitless?
So if I want to take the unitless, how y is, see, because see, sine कैसा operator होता है? Sine is an operator which gives you the ratio of perpendicular upon hypotenuse for a particular angle.
Yes sir.
Right. So obviously that ratio of perpendicular upon hypotenuse is unitless, because you will measure the perpendicular and hypotenuse in the same units, no?
Achha, okay, so basically we are inputting that 13 degrees and we are getting a unitless quantity by applying that sign.
Okay. Correct. ठीक है. और दूसरी बात देखो, यहाँ पे मैंने क्या किया ना, I have not given any unit for y, so I'm assuming that this is just sine square x. It's not sine square x multiplied with any unit. You understanding?
Yes sir.
Now यहाँ पे थोड़ा सा hidden meaning है ना? ये जो term है sine square x, I'm just taking it as sine square x. It's not sine square x into some unit. But suppose I said y is equal to sine square x, where y is in, let's say, hours, suppose, instead of just being a number. That means क्या होता है ये? This would have been actually 1 hour as a unit multiplied with sine square x, because sine square x is unitless, but I should multiply it with something so that I get y in hours. So then there would have been a hidden meaning that there's a 1 over here, which is a physical constant and it is in hours. Or suppose y was in, let's say, kelvins. Okay, y was the temperature in kelvins. So then this sine square x would mean that it is actually multiplied with 1 Kelvin into sine square x. Whatever x is, that's not important right now. You understanding now?
Yes sir.
Okay. But here I don't have to worry about that because I have not given any unit for y. So I'll just assume that y is the number which I get when I take sine square of some angle and subtract it from sine of that same angle. Okay. Yeah. Now many of you have given the answers for the radian unit also. So that's correct. Okay. Let me just verify that for you. So suppose I take in radians, x in radians. Okay. Then my x1, which is 0 degrees, would have been the same as 0 radians. But my x2, which is 30 degrees, that would be expressed as how much? Pi by 6 radians. Okay, because you know that pi radians is equivalent to 180 degrees. So just use unitary method. Or 2 pi radians is a complete circle. So it is equal to 360 degrees. Okay. So in that case, my delta y by delta x would have become y2 minus y1 upon x2 minus x1. So the numerator would have remained the same. It's minus 1 by 4 minus 0. But the denominator would have now become in radians pi by 6. So I would have got how much? Minus 3 by 2 pi. But this would have been per radian. Okay, so this would have been my average rate of change. Now you'll realize that there's no difference between this and this. This and this are absolutely the same because pi radians is equal to how much? It's 1. So minus 3 by 2 pi is the same thing as minus 3 by 2 into 180 in per degree. So you can see it's absolutely the same. There's no difference at all. So that's itna hi hai. So that's another interesting point that you can see about average rate of change. Okay. Now coming back to the geometrical representation of average rate of change.
Sir.
Yes.
Sir, I just wanted to confirm that, like you said that y was in previous question, y was like a unitless quantity because like sine is like gives the ratio of
Yes. But why I said y is unitless now, because see, I have defined the function as sine square x minus sine x, correct? Now in that I know sine x is what kind of quantity? It's unitless.
Yes, sir, as it gives.
ठीक है, तो sin square x भी कैसा होगा? Unitless है, ठीक है? And I have not said anything else to indicate that this sin x is multiplied by some unit. ठीक है? Yes. ऐसा मैंने कोई extra information नहीं दिया है that I'm suggesting that there is some hidden unit over here. So I will assume that y is a pure number. Got it?
Yes, sir. Thank you.
So for example, even if I had said y is equal to 2 sine square x minus 3 sine x, even this is a same type of function. Now, if I have not given any extra information here, then I will assume that 3 and 2 are which type of things? They are numerical constants. So if they are numerical constants, then that would mean that y is which type of quantity? It is unitless. Okay, but suppose I said that, but suppose y was in newtons. Now y is the amount of force in newtons. Then that would immediately imply that that 2 that I've written over there is actually a physical constant, and that 3 that I've written over there, that's also a physical constant. So now 2 and 3 would become physical constants. Okay, so it all depends on how we are using the function in our physics problem. Suppose we are using the function to define y as a force in terms of x as a displacement, then it will become a little bit different how the units are expressed. But right now we are not saying anything like that. So if there's no other information given, then I'll just assume that y is a number because 2 and 3 are numerical constants. Okay, so hope this point is also clear to all of you. Yes. Yes, Nishchay.
Thanks, sir.
Sir, in that last question, after we got minus 3 by 2 pi radian, sir, then we will multiply it with 180 by pi, right? To get it in degrees.
Yeah, I mean, see, if you want to convert it to per degrees, na, so that means the pi radians has to be changed into, I mean, this whole number na, has to be changed to degrees. Na. So it's like inverse of this. Na. So 2 pi by 3 radians is how many degrees? It's equal to 2 by 3 into 180. Or it's 120 degrees.
So how is
because
this inverse?
Pi radians is equal to 180 degrees. Na? That is the conversion factor. No?
The minus 3 by 2 pi, मतलब कैसे reverse?
See, look at this. 2 pi by 3 radians कितने degrees होते हैं? 120 degrees होते हैं कि नहीं?
Yes, sir.
So 1 upon, see, this is minus 1 upon 2 pi by 3 na, per radian. Because remember, radian is in the denominator. Na?
So radian has to be in the numerator. Then only we will be able to convert it, right?
Yeah, I mean, see, it is per radian. Na? So it's like if I said that it is 60 kilometers per hour. So how will you convert this to kilometers per minute?
Sir,
You will
hours
divide this by
into
60 now, because this is 60 kilometers in 1 hour. Now you will convert that 1 hour into 60 minutes now. So that will mean it's 1 kilometer per minute.
yes, sir.
No, so same kind of thing. No? It is so many per radian. So how many per degree? You will convert the radian to degree. So you'll use the conversion factor that pi radians is equal to 180 degrees.
Okay, sir.
Yes, sir. Okay.
That means directly we cannot do like minus 3 by 2 pi into 180 by pi. That will not yield
Because
us a
wo kab hota? See, if I said it is minus 3 by 2 pi radians, okay, then it would be equal to minus 3 by 2 pi into 180 by pi degrees. But this is not that case. No? This is the case where it is minus 3 by 2 pi per radian. No?
Sure. Yes, sir.
Got it, no? So there's a difference between this and this. No?
Yes, yes, I got it.
Okay, so this is also something we have to be alert about, especially in future when we are going to apply functions in physics. You know? So we have to be careful about units. In fact, there is a whole chapter based on this. You might have seen in, if you've gone through standard textbooks like your NCRT or even HC Verma and all, you'll see that even before calculus, sometimes they start with a chapter called units and dimensions. ये chapter देखा है आपने कभी?
Yes, sir.
Yes, sir. बहुत
So
बड़ा
this,
NCR.
Yes, sir.
yeah, it's a very big chapter, in fact, and it deals with many systematic methods of conversion of units, the relationship between units of different things, etc. Like how to convert 1 kilowatt hour into watts. What kind of physical quantity is kilowatt hour for?
Energy.
Yes, it's for energy, because okay, sorry. So we'll convert it into joules, let's say, okay, or convert it into horsepowers, etc. So these kind of things, we will learn in a whole separate chapter. So we will do that chapter here also, okay. But right now it is important for us to master vectors and calculus first. So that's why we start with that. So you learn some more techniques about this conversion of units and all in that chapter, okay. Now coming back to average rate of change of a function. So as we saw, there is the graphical interpretation, which was important. So the graphical interpretation became that it is the slope of the secant line. So if we have the graph of a function, so this curve represents the function. Now I want to find the average rate of change between x1 and x2, let's say. So all I'll have to do is plot the point on the curve which has x coordinate equal to x1. So from this I'll get the y coordinate y1. Then plot the same point, similar point which has x coordinate equal to x2. So from this I will get the y coordinate y2. And then I can see that, okay, the definition of average rate of change is such that if I draw a straight line joining these 2 points, then the slope of that straight line itself is nothing but the average rate of change. Okay. So now in this right angle triangle, this one here, you can see that this perpendicular is actually your y2 minus y1. And this base is your x2 minus x1. So now you can convert this into a geometrical fact that the value of delta y by delta x for that interval, which is y2 minus y1 upon x2 minus x1, just happens to be tan theta. And that is the same theta that this particular straight line, wherever it meets the x-axis, whatever angle it makes, this theta is the same as this theta over here. So it is nothing but the slope of the secant line. So this becomes also a very important way of understanding what is the average rate of change. Average rate of change is slope of secant line. And what is the definition of secant line? As we saw last time, secant line is a straight line that joins two distinct points, or two individual points A and B, which are far from each other. They are not like consecutive points. Now you might say far from each other se mera kya matlab hai? How far from each other? So there's no answer to that question. Mathematically far from each other basically means, or two distinct points means that they should not merge into each other. That's all it means. Okay. So why this definition also becomes important? Let's see an example question. Okay. Now suppose this is the type of question I had asked you to explore in this thing also, in the exercise also. So suppose we have a question like this, that a particle starts from rest at t equal to 0, okay, has uniform acceleration of, let's say, 5 meters per second square for 10 seconds, okay, then moves at uniform speed for 10 seconds, and then decelerates at 2 meters per second square. Okay. Now I ask you, find the average speed from 0 to, let's say, 25 seconds. 0 to 25 seconds. Now, what is the best way to interpret this question? Just try this out.
Sir, it decelerates at 2 meters per second square?
Yes.
Okay.
And then that is after this further 10 seconds, it decelerates at 2 meters per second square uniformly. First it accelerates uniformly at 5 meters per second square. Then for some time, that is another 10 seconds, it moves at uniform speed. And then it decelerates at a uniform rate of 2 meters per second square. So what is the average speed from 0 to 25 seconds? Yeah, anybody got the answer for this?
Sir, 1 minute, sir.
Okay. So continue on how you're working on this, but I will just give you an easy way to understand this. Okay. So if I talk about the speed versus time graph, that's not distance versus time, that's speed versus time. Now what I can interpret about speed versus time graph, that the speed is starting from 0, increasing uniformly at the rate of whatever 5 meters per second square for 10 seconds. Okay. Then thereafter it is constant for 10 seconds. Okay. And then it is decelerating much more slower at 2 meters per second square. It should be something like this. So this speed, let's say V naught, this will become how much? 50 meters
Yes,
per
sir.
second. Okay. And then if it is decelerating at -2 meters per second square, then 50 to 0, it should take 25 seconds. Okay. So I also know that there should be another interval of 25 seconds from here to here. That means the total time of the journey, assuming it finally comes to rest, will be 45 seconds. Okay. Now from this graph, how will I convert it to the graph of the distance versus time graph? Because that's the one I need now. So already using the concept of instantaneous rate of change, which I haven't talked about yet today, okay, but just using the information that we had from last time, you will see that we get an intuitive feel of how this graph should look. Here pe see the speed is increasing. So that means the distance should increase in such a way that the slope of that graph should be increasing. So it should be a graph like this. The slope is increasing till we reach the time of 10 seconds. Then what happens? The slope is constant. So for some time, the next few seconds, which is 10 seconds actually, the slope should be constant. So it should be like a straight line. So if I were to draw it exactly, in fact, it could be something like this. And then it starts decelerating. So if I draw it, till it comes to rest. Okay. So when it comes to rest, the distance should become, it should almost become a horizontal line. Okay. So this is what is happening for the first 10 seconds. Then this is what is happening for the next 10 seconds. And finally, it's coming to rest somewhere over here. So for the next 25 seconds, this is what is happening. Okay. Now the whole question is, okay, now we are talking about 0 to 25 seconds. So I'm talking about this time over here, somewhere here. I need to know this point. So if I know this point, then the answer to my original question becomes it is the slope of the secant line joining 0 to 25 seconds. So I then want to find, in terms of geometrical representation, what I want to do is I want to plot this line and find its slope. Okay. This is my secant line for 0 to 25 seconds. So I want to find this tan theta. So now, can someone give me an easy way to calculate this distance? At 25 seconds, what is the total distance covered?
Sir, we can calculate it from
Sir,
velocity.
I got it 7.
Sir, can we use kinematical equations?
Sir, I got
Yes,
7.
you can definitely use, in fact, that is what, okay. Okay, I'm getting quite a few answers. I will just verify the answers. But I will tell you the easy way which I feel. Okay, the easy way that I feel to get this is area. I just need to calculate this total area. This total area now, this area represents S from 0 to 25. Is that correct?
Yes, sir.
You're familiar with this concept, and the area
Yes,
under
sir.
the V versus T graph gives you the distance covered, speed versus time. So that's probably the easiest method. Otherwise, we can do it from kinematics equations also. Okay. So how to calculate that area? You can break the graph into smaller bits. Okay. So this area will be area from, let's say, 0 to 10 plus area from 10 to 20 plus area from 20 to 25. Okay. So this will be very easy. Half base into height. This will be very easy. Area of rectangle. Okay. This will be a little bit tricky. So let's come to this part. So at 20 seconds, you can see that the velocity is 50 meters per second. And then it's having a deceleration of 2 meters per second square. So at 25 seconds, how much will the velocity have become? Would have become 50 minus
40 meters per second.
2 into 5. Yeah. Is that correct?
Yes, sir. I said 40 meters per second.
40, no? You said, huh? Correct. So,
Sir, we can use half 80 square also, right?
We can use that also. But then we will have to use it in parts now. Okay, so I'll explain that method also. So this is that area of the third part that I'm talking about. This area. This is the area from 20 to 25. Okay. So for that, I'll use the formula half sum of parallel sides into perpendicular distance between them, which is 5. Okay. Trapezium. I'm using this area of trapezium. In this case, this is a trapezium like this one. So if this length is A, this length is B, and this perpendicular distance between the two parallel sides is this, then the area is half sum of parallel sides into the distance. Now, the interesting thing is a lot of these formulae which you take for granted in mathematics, okay, in geometry, their derivation actually also can be shown from calculus, and this we'll be doing in a few months. I mean, in a few weeks. Now we'll see how this formula actually came, how the formula of area of circle is pi r square, how the formula of area of ellipse is pi ab. All these formulae we can see from the application of calculus itself. Okay. Okay, so this is becoming how much? This is becoming 500 by 2, so that's 250 meters. Okay, this is becoming 500 meters, and this will become 45
225.
into 5 by 2. Sorry?
225.
How much is 225? Okay. Okay. So the total area or the total distance traveled from 0 to 25 is becoming 975 meters. Is that correct?
Yes, sir.
Just check this last calculation once. Okay. Okay. So now I know this value. From here, I know this value is how much? 975 meters. Okay. And this is, so now I know that the slope of the secant line okay. So I'll know that average speed, which is total distance upon total time. Okay. But for 0 to 25 seconds, so that is becoming 975 divided by 25. So that is further how much more?
39.
39.
39.
39 meters.
Yeah, very good. So number of people got it correct in the first time only. You had given me the answer. Very good. So it's becoming 39 meters per second. Okay. So what I feel is this is probably one of the easiest and most intuitive ways of doing this problem. Okay. Where in fact, I have gone a little bit beyond what we've learned in terms of rate of change. I've gone into another important concept in kinematics from before, that if I have a speed versus time graph, then the area under the graph gives me the distance. Or if I have a velocity versus time graph, then the area under the graph gives me distance. But what is the important point here is that to plot the speed versus time graph, I've used the concept of rate of change. I've used the concept that there is a uniform and positive rate of change initially. That means the speed versus time will be looking like a straight line with a positive slope. Then there is zero acceleration that is moving at uniform speed, so it should look like a horizontal line. And then it's decelerating uniformly. That means it should look like a straight line with a negative slope. So that is the concept of rate of change that I've used in this particular problem. So somewhere or the other, the concept of rate of change is becoming very important. Okay, now I'll just give you a brief hint how you could use formula-based method for solving this. Okay, just a brief hint. So you could also do it this way, that from 0 to 10 seconds, what is happening? The initial velocity is 0, the acceleration is +5. So the displacement, let's say S1, you could just use this. So that would come out to be 250. Then from also the final speed would come out to be 50 meters per second at t equal to 10 seconds. This would be the instantaneous speed at 10 seconds. This would be from 0 to 10 seconds. That would be the distance traveled. Okay. Then from 10 to 20 seconds, what is happening? The speed is 50 meters per second, which is this speed. Okay. But the acceleration is 0. So distance is just speed into time. Okay. And then from 20 seconds onwards, what is happening? It is having a uniform deceleration of 2 meters per second square. Okay. And its initial velocity is this speed only. So that is 50 meters per second. So, okay, so this is from 10 to 20 seconds. Okay. So S3 would be
Sir?
yeah. So in this now we will use this relation now. So it is 50 into, now suppose I'm calculating this S3 from 20 to 25 seconds. Okay, so that is an interval of 5 seconds. So -2 into 5 square. So I'll have to do all this, and this would come out to be, you'll see when you calculate, this comes out to be 225. So you'll get the total distance as S1 plus S2 plus S3. So you get that as 975 over and divide it. So this would be, you'd have to divide the motion into 3 parts and like that. Okay. All right, now from the business of rate of change, now we come to the most important point, instantaneous rate of change. From average rate of change, we come to the main, crux of the matter here for us in differential calculus, which is instantaneous rate of change. So today we will start with a proper technical definition of instantaneous rate of change. Okay, we will start by giving it a separate symbol altogether. We will use now the calculus terminology or the calculus notation for it. In the calculus notation, the instantaneous rate of change for a function y is equal to fx, it is denoted by a new symbol dy by dx, where this means the rate of change of y with respect to x for a very, I can go on writing very actually, and that would not be enough to explain what I mean by it. So, but I'll stick to just two varies. So for a very, very small interval such that small interval dx, okay, such that dx is equal to delta x under a certain condition, and that condition is called a limit that delta x tends to 0. Okay, so now let us understand the meaning of this. Okay, so if this is my x-axis, okay, now if this point is a particular value x, okay, so this point is, let's say, x plus delta x. So the interval between these 2 points, this interval is my change in x, that is delta x. Okay, but now if I want to interpret this in context of instantaneous rate of change, it becomes virtually an impossible task in terms of geometry. It's just like an abstract idea that if I magnify this a whole lot of times, so let's say I magnified it to, okay, so then let's say this point now is my point x. So now this point right next to it, this should be x plus dx. So as I said, it's a very abstract idea. It's not something very easy to visualize. Okay.
Sir, it will be x plus delta x, right? Not dx.
No, so that's what I'm now defining as dx. Till last time, we were still in the notation of delta x, but now we are getting into the technical notation. Okay, so this point and this point are so close that the distance between them is becoming technically what we call as dx, which is nothing but delta x in the limit that delta x is tending to 0. So it's so small that these 2 points are almost merged into one point. So when I zoom out of this, you can see that those 2 points are almost the same point. Okay, so that is a difference between a change in x, which is delta x, and a differential change in x, which is dx. That is the difference between these 2 things. When we have a standard value of delta x, it means we have 2 distinct points like x and x plus delta x. But when we have a differential change, okay, so this is called a differential change. The proper name for it calculus wise is that it is a differential change in x, whereas this is a change in x. This is simply change in x. So what is a differential change? A differential change in x is a change so small that its value tends to 0. It is as close to 0 as we can imagine. Understood now the difference between delta x and dx?
Yes.
So it is it's quite it's a lot about imagination actually. We really have to imagine that it's even closer than the two dots that I've shown over here, because it's so close that we cannot actually draw it. They're almost merging into the same point.
So like delta x like is a change, but dx is a very small change, very small
Yes,
change.
yes. So it's such a small change that now it is given a special name, and that special name is differential change. Okay, so differential change means a change in x so small that its value tends to 0. Okay, so we are learning this new term now, that dx is a differential change. Okay. Or we can also call it an infinitesimal. Okay. So this is a special symbol that we use from differential calculus, dx. Okay. So now, of course, physics is a practical subject which has to do with real life measurements and real life physical quantities. Okay, which so it comes down to really the relationship between physical quantities which are tangible and which can be measured. So in that practical sense of physics, we mean that dx is such a small interval that it's the smallest interval that we can measure. So for example, if x was on the time axis and we are measuring the instantaneous speed, then the smaller the interval for time for which your speedometer can actually record the distance covered, the better my calculation of dx will be. If it is 1 microsecond, then so be it. But if I have another speedometer which can go up to 1 nanosecond, then the second speedometer is that much more accurate compared to the first one. It's literally 1,000 times more accurate, because 1 nanosecond is 1,000th of a microsecond. All right, so now when we come to graphical representation of instantaneous rate of change or graphical interpretation, we see that even that is a very abstract idea. It is just an idea. There is no formula from the graph as such. So from now, we will just use this symbol and we understand that what it means, instantaneous rate of change. So what we mean by the graphical interpretation of this now is that what we discussed last time only, that if we have the curve known to us, because we have plotted it using ordered pairs and all that. So we have some known sort of curve which represents the function y is equal to fx. But now at a particular value of x, like let's say this one here, at a particular value of x, I want to find instantaneous rate of change. At a particular value of x, let's say x equal to x naught, I want to find that. So this one is the x naught. So again, like in terms of interpretation, what we'll have to do is that we'll have to go zoom into that point, okay, and we'll have to plot the very next point after it, which will have an x coordinate equal to x naught plus dx. Okay, so that this quantity here, this interval, this is equal to delta x with the limit that delta x tends to 0. So now we will have to do literally that impossible task. At least geometrically, it's impossible to do it without help of some further mathematics. But we'll have to join these 2 points. As you can see, that's a struggle. Okay. With a straight line. Okay, let me see if I can use a narrower gauge. That might help me. It's a little bit easier maybe this way. So this, as you can see, becomes a task of imagination. Okay, I can't really rely on this as a problem solving method, that every time I'm given a graph, I'm able to actually, I'm able to zoom into it and plot 2 separate points. This is not going to be a practical method of how we can. So the idea here is that what we should do is we should draw a tangent at the point x equal to x naught. That is a line that connects x equal to x naught with the next consecutive point at x equal to x naught plus dx. Now we are using that language of dx. So when I do that, then dy by dx will be nothing but slope of tangent. Okay, so you can see that this is the geometrical definition of it, or the geometrical interpretation of it, but it's very abstract. It doesn't really give us a practical way of solving for this. Okay, and that is why we have to develop a whole new brand of mathematics, a whole new machinery in mathematics, which we call differential calculus. Okay, and we will make good progress in differential calculus today itself. You will see that for certain simple types of functions, we will just have a simple formula based process through which we'll be able to calculate the slope of tangent. Okay, so as you can see, this is an abstract idea. This is not very practical in terms of actually calculating the rate of change. So this is an abstract idea. It does not give us a direct method to calculate instantaneous rate of change. So instead, what we do is we go back to the definition. So now we come to differential calculus. And we understand that differential calculus is a new operation in maths, which gives us a method for directly calculating the instantaneous rate of change. So this is an operation which gives a direct method to calculate the instantaneous rate of change. For a given function by using certain algebraic type of principles. Okay, so that is what is differential calculus. So in differential calculus, the first operator we will learn about is the differentiation operator. And that operator is given by the symbol d by dx. So it looks like a fraction, but this symbol should be read as it is differentiation with respect to x. This is how we read this symbol. Okay, this symbol d by dx, it is read as differentiation with respect to x. Okay. What this operator does, this operator, okay, when applied to a function y is equal to fx, okay, gives a formula for its instantaneous rate of change. Yeah, I'm coming to you, Nishchay, just a minute. Okay. dy by dx. So when we operate this on a function, it directly gives us an algebraic formula for the instantaneous rate of change. Yes, Nishchay.
Sir, how many operators are there for differential calculus? Only one, right? This differentiation.
Yeah, I mean only one in the sense that here we'll be talking about functions of single variable. So there'll be only one operator, which is d by dx, or differentiation with respect to x. Little bit later, 3-4 months from now in physics, we will learn also about something called partial differentiation. When we have a function of more than one variable, like temperature at a point might be a function of x, y, z coordinates. So there are 3 independent variables, x, y, and z, and not just one independent variable x. So there we will learn of more operators like partial differentiation or partial rate of change with respect to x, y, or z. But we don't need to worry about that right now. Okay. Right now, when we're talking about differential calculus, there's just a single operator for rate of change, which is rate of change or differentiation with respect to x.
Okay, sir.
So we use like partial differentiation, explicit and
Yes, Dhruv,
implicit function.
Dhruv, can you speak a little bit closer to your mic or louder, please? I can't hear you.
Sir, your voice is breaking. I can't hear you, sir.
Dhruv, I'm not. Just try again. Yes, Dhruv, you had some question, beta? Okay, if you're having difficulty with the mic or whatever, you can send me the question on chat message also. I'll help you out. Okay.
Sir,
Yes.
what do you mean by the word formula
So I'll
in
explain.
the last sentence?
Yes. Okay. It gives us a direct formula from which we can find the instantaneous rate of change. Okay. So before I come to the explanation of that, again visualize this, what it means. It's like the operator is like some kind of process. It's like some machine, okay, which is the differentiation operator. Okay. So again, when we input the value of a function, okay, it directly gives us the output, which is the differentiation operator applied to that particular function. And this output, this is nothing but the instantaneous rate of change for the function fx. Okay. So our input into the operator is the function fx, and the output is the instantaneous rate of change of the function. So this is the process that differentiation is giving us. How it's giving us, we haven't come to it. No, but let's understand what is the process. No. Like any operator in maths, you input something, it gives you some output. You know? So for example, if I have the operator, which is the mod function, okay, this is the modulus operator instead of differentiation. So what is the meaning of this? That when we input a variable x, the output that we get is mod x. So if we take x equal to 1, mod x becomes 1. If we take x equal to minus 2, mod x becomes 2. If we take x equal to plus 3, mod x becomes 3. It's a quantity without an algebraic sign. So that's an example of the modulus operator. Okay. So like that, this is the example of the differentiation operator. So what it does, it gives us a formula from which we get the value of the instantaneous rate of change. Okay. Now, how we get this? Let's understand. How does the operator achieve this? Okay, it achieves this by developing algebraic formulae from the definition of instantaneous rate of change. So that's a very interesting thing, and that's what we'll look at next. Okay, so I hope that answers your question to a certain extent. Exactly how we haven't seen, but what it does we are understanding now, right?
Yes, sir.
Okay. So definition of instantaneous rate of change. We have seen this is a definition that it is with a special limit or a special condition that delta x should be tending to 0. It is the value of delta y by delta x. So it is with the condition that limit delta x should be tending to 0. If we are calculating for the function y is equal to fx, it is f of x plus delta x minus fx upon delta x. Come to this formula, okay, that I know that delta y by delta x is equal to y2 minus y1 upon x2 minus x1. So if I take x1 as x and x2 as x plus delta x, okay, then delta y by delta x will become f of x plus delta x minus fx divided by delta x. So this is the definition of rate of change, average rate of change. Now in that average rate of change, I'm just putting the special condition now. I'm putting the condition that limit delta x tends to 0. So the moment I put that condition, now what happens? My delta y by delta x becomes equal to what? It becomes dy by dx. So this is the definition. Okay. So as a simple example, any linear function, we had discussed that day, y is equal to mx plus c, where m and c are constants. Okay, we have the formula that this will become equal to m. Okay, now we'll see the proof of this very soon, but just write this down first. So there are two ways of proving this formula now. One is from the geometrical interpretation, which we had seen in the previous lecture itself, that if you have a linear function, what does the graph of the linear function look like? It looks like a straight line. So the tangent drawn at any point on that straight line is that line itself. So whatever is the slope of the line will become the slope of the tangent. So it's like a very simple argument that the instantaneous rate of change should be equal to the slope of the straight line itself. But we'll also see the proof of it by using this definition. This is the algebraic definition.
Sir, this in this case, sir, average rate of change will be equal to instantaneous rate of change also, right?
Very correct. Yes. Average rate of change for any interval of time. or any interval of x will be equal to instantaneous rate of change at any particular value of x, and that will be equal to nothing but the slope of the straight line itself.
Sorry, I got disconnected. So could you please repeat like what you were saying?
Yeah, so we are talking about differentiation, what it does basically. Okay, so we have to think of differentiation as an operator. Okay, this is the symbol of the operator, that when we input the quantity fx as a function, the output that we get is rate of change or instantaneous rate of change. Okay. And now we are coming to the important thing, how we achieve this in differentiation. Okay. So how it does it? It does it by developing a set of algebraic formulae from the definition of instantaneous rate of change. So what is the definition of instantaneous rate of change? This is the definition. This is the algebraic definition. Okay. So as a first example, we are looking at a linear function. Okay. So for the linear function, the proof is very simple. How we'll prove it? One is we can go with a geometrical proof, or the other is we can prove it algebraically. And both are equally easy. Just have to visualize it. So geometrically, the proof is like this, that we know that the graph of any straight line or graph of any linear function will be a straight line. So we have the function y is equal to mx plus c. Graph obviously looks like a straight line. So it's a straight line graph. So whether we are looking at two distinct points, or we are looking at a particular point and we are drawing a tangent at that point, whatever we are doing, we can see that the secant line between any 2 points at x equal to x1 and x equal to x2 and tangent line at any point coincide with the graph, which is the straight line itself. Okay, so therefore slope of secant line equals to slope of the tangent line equals to slope of y equal to mx plus c. So delta y by delta x for any interval equals to instantaneous rate of change at any point equals to m. So from this point onwards, we don't have to think twice about this also. We know that whenever we are dealing with a linear function, we're dealing with a straight line graph. So obviously its instantaneous rate of change is equal to average rate of change. Okay, but let's see the same thing, how we prove it algebraically. So algebraically, how we prove, how we take dy by dx, it is the limit that delta x is tending to 0 into f of x plus delta x minus fx divided by delta x. Now here, what is fx exactly? Fx is mx plus c. So let's just substitute. So this is the limit delta x tending to 0, m of x plus delta x plus c minus mx plus c divided by delta x. So that is limit delta x tending to 0. So you can see mx plus c will cancel, m delta x divided by delta x. Now remember here that delta x is tending to 0, but it's not equal to 0. So it's not a 0 by 0 actually. It is like m into some very, very small quantity, like 10 raised power minus 50 divided by the same quantity, 10 raised power minus 50. So these two will cancel. Okay, so we can cancel them because remember delta x is not equal to 0. Delta x is tending to 0. There's a difference between the two. If it was equal to 0, then we could not cancel because 0 by 0 is undefined. But in this case, it is tending to 0, but not equal to 0. So we can see it as m. So dy by dx, the instantaneous rate of change, hence true. Okay. So whether we think algebraically as per the definition of instantaneous rate of change, or we think geometrically as per the geometrical interpretation of instantaneous rate of change, that is slope of tangent, it's very, very easy to understand why the rate of change, instantaneous rate of change of a straight line graph or of a linear function should be equal to the slope of the linear function, should be equal to m. Okay. So for example, if I have y is equal to 5 minus 2x, then I know that dy by dx, the instantaneous rate of change, is nothing but minus 2. If I have y is equal to 3x plus 8, I know that dy by dx will be plus 3. And it's very easy to visualize this in terms of this graph, but also it's equally easy to justify it algebraically. That if I'm calculating the rate of change for a very small change in x, its value will still be equal to m.
Sir, can you please explain the third step again?
This one where I've cancelled the delta x.
Yes, sir.
So see, just expand this bracket now. Expand this bracket above. You'll get mx plus m delta x plus c minus mx minus c.
Yes.
So what will remain in the numerator? Only m delta x.
Yes. Okay, understood.
Okay, and then why is it justified to cancel the delta x? That's the more important thing, because delta x is not equal to 0. It's tending to 0, that's fine, but it's not equal to 0. So it's justified to cancel the delta x.
Okay, sir.
Okay. Now next, very interestingly, we'll see that if we take the function y is equal to x cube, okay, then we want to find out what is dy by dx. Okay, so when we study the set of formulae, we'll see that this is given by a simple formula, that rate of change of x cube. Okay, some of you might be familiar with this, some of you might not be familiar. It doesn't matter.
N multiplied by x raised to x minus 1.
This is the formula given for it. But now I want to see what is the proof of this formula. What is the justification of this formula? So I'll go with this definition, that it is limit delta x tending to 0 of f of x plus delta x minus fx divided by delta x. And here the function itself is x cubed. So for this function, the instantaneous rate of change is the differentiation operator applied to this function. So that is nothing but limit delta x tending to 0 f of x plus delta x. So that is how much x plus delta x cube, okay, minus f of x, which is x cube, divided by delta x. So I have to just simplify this algebraically. So it's not as easy as the linear function, but it's not very difficult either, because I know the formula that a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube. We know this formula now. So just use this over here. So it is limit delta x tending to 0, x cube, okay, plus 3x square delta x plus 3x delta x square plus delta x cube. Okay, so that's this one. And then I have minus x cube, the whole thing divided by delta x. So now open the bracket and see what we are left with in the numerator. We are left with these terms: 3x square delta x plus 3x delta x square plus delta x cube, the whole thing divided by delta x. So as I said, it's a little bit more complicated, okay, but still not that difficult, because now what I can do is I can take delta x common in the numerator. So I'll have 3x square plus 3x delta x plus delta x square, whole thing multiplied by delta x divided by delta x. So now remember that delta x is not equal to 0. Delta x is only tending to 0. So I can cancel this. Okay. So now I'm left with this term, that delta x is tending to 0 and the quantity itself is 3x square plus 3x delta x plus delta x square. So if delta x tends to 0, it means that this term, it tends to 0. This term, it tends to 0. So these two terms are negligible compared to this term. So what I'm left with ultimately, I'm left with 3x square. So what this is showing me, that differentiation of the quantity x cube is given by a simple formula, that is 3x square. Yes, Nishchay.
Sir, for general x to the power n, we have to use binomial theorem, right?
Yes. So the same thing now, if we expand it by binomial theorem. Now many of you may be familiar, may not be familiar with binomial theorem. So I'll explain that later also. Binomial theorem is a general theorem through which we can expand a plus b to any power n. Okay, so this is given by something called binomial theorem. So we don't exactly need binomial theorem yet over here, okay, but I'm just saying here we have used a special case of binomial theorem, n equal to 3, we got this formula. If n is equal to 2, you know the formula is this one. Yes, Nishay, you have a question, beta?
No, sir, I already.
Sorry, Dhruv, my mistake. Yeah, Dhruv, you have a question, beta?
Yes, sir. So, like, how do we visualize this one, like graphically? Like,
I'll explain that. I'll explain that also, how we visualize it graphically. But first, just, all of you just go through these steps once carefully. Each and every step you go through it carefully. I've tried not to skip anything. I tried to give you a very systematic step-by-step explanation of it. Okay. See, ultimately for us, what will be important will be this formula. This derivation will not be important for us when we are solving physics problems. But at the same time, we should have some idea of how we have got this formula. We should not just blindly learn the formula. There should be some justification that we understand of it. So that's why these few examples, we will first learn how the formula came from the definition of instantaneous rate of change. What was the definition? The definition was this. So applying the fundamental definition of instantaneous rate of change to this particular function, algebraically how we are able to justify. This is how we are able to justify कि मेरा instantaneous rate of change ये हो जाएगा.
Sir, can you please tell means how did you remove the limit sign outside the brackets?
How I remove the limit sign? Na? So now see, now the point is delta x is something as small as you can imagine. So tell me the smallest value of delta x you can imagine. Just think like arbitrarily and tell me. Any suitably small value of delta x, just think and tell me.
Sir, 0.00001.
Okay, 0.00001. This is what you said, right?
Yes, sir.
Okay. तो अभी देखो x का वैल्यू कुछ भी हो, but ये delta x का अगर वैल्यू ये है, then this quantity, this second term, will be much smaller than the first term.
Yes.
And the third term will be even much smaller, because the second
Yes,
term
squared.
has this delta x which has 5th place of decimal. The third term will have 10th place of decimal. Okay, so we can easily drop these two terms. They are neglect. Now see, this is for this only. This is still quite an ordinary small number. An extraordinary small number would be like let's say minus 10 into 10 to the power minus 20,000. Let's say. Now can you imagine if I take something like this, how small these two numbers would become? It'd be as good as zero, no?
Yes.
So that's the justification. How we can drop the limit delta x tending to zero. Okay. Whereas here you can see that if I put limit delta x tending to 0, there's a problem because I have 0 in the denominator. So I cannot directly, I have to get rid of that delta x in the denominator. Then only I can apply that, okay, for practical purposes, delta x is 0. Okay, now let's understand this graphically, what we mean by this. Now remember I told you earlier also that instantaneous rate of change being slope of tangent, it gives us an idea in graph. It just gives us an abstract idea. It does not give us a method to actually calculate the slope. Now what is the method to actually calculate the slope? In fact, since we are talking about y is equal to x cube, let's draw a graph like this. So I will not get into too much detail of plotting the graph. That you can try out yourself and see later. But you will see that this graph also goes something like this. Okay. Because on the negative side, it's like a reversed mirror image. It's an inverted mirror image. Like this. So at +1, if the value is 1, at -1, the value should be -1. Then by the time we go to 2, it should rise very rapidly to 8. -2, you go to -8, and so on and so forth. Okay. So this is the graph of y is equal to x cube. Okay. So what this now means is that if I take any arbitrary point x, any arbitrary point x suppose, and I draw a tangent line at that point. Now imagine that from that point I'm just drawing a tangent line. So this is the tangent at some x equal to x, let's say. Or let's say it's at some x equal to x0. So this value of x was x0 here. This point, okay. Then the slope of the tangent will be equal to 3x0 square. Okay. So y is equal to x cube means that instantaneous rate of change is the differentiation operator applied to x cube. So that is 3x square. Okay. So that means at x equal to 0, for example, this will be 0. So slope of tangent is equal to 0 at x equal to 0. Okay. But at the same time, at x equal to 1, it will become 3 into 1 square. So it will become +3. So this is the slope of the tangent drawn at x equal to 0. Sorry, x equal to 1. In comparison to this, if I draw the tangent at x equal to 2, that will become gigantic in comparison. It will become 12. You can see why this is happening, because the shape of the graph itself is such that so if I, for example, draw a tangent line at x equal to 0, it will be a horizontal line. If I draw a tangent line at x equal to 1, be like this. Okay, but if I draw a tangent line at x equal to 2, for example, now that tangent has a steeper slope. So this exactly gives us how much that slope is. Okay. This is the tangent at x equal to 2. So this one has a slope equal to plus 12. Whereas this one, yeah, Nisha, I'm coming to it, is the tangent at x equal to 1. So this one has a slope of plus 3. Yes, Nisha.
Sir, can we link the difference of rate of change in these different, like they are coming in an AP, like 12 minus 3, 9, then 6, 15.
Yeah, there is a symmetry in the formula. It's not exactly AP, so I'm coming to that. Okay, so I'll come to the general expression also. So there is a symmetry to it to a certain extent. Yes. Okay, so I hope the geometrical interpretation of this is now clear. So for y equal to x cube, the instantaneous rate of change. So this process that we've got, this is by differentiation. By applying differentiation, we have learned that if y is equal to x cube, that means dy by dx is equal to 3x square. So at any point, if I'm drawing the tangent, the slope of the tangent should be equal to the value of 3x square for that value of x. This is the meaning of the instantaneous rate of change.
So we can apply this to find the instantaneous velocity also, no?
Yes. So for example, if I had this equation where my displacement was equal to, let's say, t cube as a function of time. So that means my instantaneous velocity would be ds by dt. This we will learn in kinematics later, but that would be differentiation with respect to time of the function t cube. So now t is playing the role that x played earlier. That's the only difference. Rest everything is the same. So this will become 3t squared. So you can see that at t equal to 0, its velocity will be 0. But at t equal to 1 second, its velocity would become 3 meters per second. At 2 seconds, it would have increased to 12 meters per second, and so on and so forth. So we'll come back to physics examples later. Okay, first let's make some progress with differentiation of general functions first. Okay, so now our first formula for differentiation. First formula for differentiation is that differentiation of x to the power n is given by the formula nx to the power n minus 1, where n is any real number. Okay. So for example, if y is equal to x squared, then instantaneous rate of change is the differentiation of x squared. So that will become 2x to the power 2 minus 1, or that will become 2x. And we have seen the proof of this last time when we took those very small intervals So you can refer to notes of calculus lecture 1 for the proof of this, how we got this. Okay. Similarly, we saw today, so it become 3x square. But let's take another example. Suppose we have y is equal to square root of x. Then instantaneous rate of change will become differentiation of x to the power half, because square root of x is x to the power half. So that will become half into x to the power half minus 1, which we can write as 1 upon, yeah, okay. So we can say that the rate of change is 1 by 2 root x. Okay. Or we can write this as x to the power minus half by 2, or we can write this as 1 upon 2 into x to the power half. These are all correct. Okay. But one way of expressing it is that it's 1 by 2 root x. So any real number power of x, we can differentiate by using this general formula. So this is the first general formula for us. Which is differentiation of x to the power n. Okay, so after you written this down, just attempt the last example as a question. Write it down. I'll put up the solution in just a bit. Yes, very good. Mansi, Agrima, Nishchay. Nishchay, you have to just check the algebraic sign of your answer once. Okay. Saina, Dhruv, Vedant. Okay, so at this, yeah, this one. Sorry, beta. What was your question?
No, sir, I was asking where was the question. I did not see.
It's the last one. Huh? This one is the question. Okay. Yes, Aryan, very good. That's correct. Nishchay, your answer is correct. Good. So let's see how we'll apply this now. Okay. So we are given this, and from this we want to find out this. So instantaneous rate of change, we don't have to do anything else, but just directly apply the formula. So we have to first express this as some power of x. So 1 upon x square, as you know, by method of indices, it will just be expressed as x to the power minus 2. Because we are just using the simple principle that 1 upon x to the power a is equal to x to the power minus a. X to the power a by x to the power b is equal to x to the power a minus b. Okay. x to the power a into x to the power b is x to the power a plus b. These are the simple rules of indices, which also actually, if you are ever doing a revision of these, you should think about how you will prove these. Okay, you can see how we prove these things also. That's an interesting exercise in maths. Now we'll use the formula that differentiation of x to the power n is equal to nx to the power n minus 1. So this particular formula we'll be applying here now. It's very simple. It's just a step-by-step process. So n x to the power n minus 1. So that is n ke jagah minus 2. So you're just getting the simple formula that it is minus 2x to the power minus 3. So it's actually just okay to just write the answer like this also. We don't need to do anything else, but we can just take it one step further. So we can also express it like this, that it is minus 2 by x cube, because it just looks nicer on the eye. Okay, when we take the power of x as a positive quantity than a negative quantity. So this is, you can say, a slightly better way of expressing than this, but there's nothing wrong with this also. Okay, your final answer is correct if it's this also. Okay, so this is the rate of change. Okay, so now I know that therefore slope of tangent at the point x equal to, what was it, 2, that will be nothing but the value of dy by dx at x equal to 2. So that is minus 2 divided by 2 cube. So that is minus 1 by 4. That's it. That's the answer to the second thing. That what is the slope of the tangent at x equal to 2? So this is the answer to it. Slope of the tangent at a particular point is nothing but the value of the rate of change, the value of dy by dx at that value, at that particular point x equal to 2. Okay, so I hope this is clear to all of you. Okay, so like this
Can
now.
you just go up for the second?
Yes, sure.
Okay, sir.
Is clear now? The method is clear?
Yes, sir.
Okay, very good. Okay, so now you will see that along with this direct formula, so the basic formula that we have, that differentiation of x to the power n is equal to nx to the power n minus 1. This is the formula we have. Now along with this, you'll also see two other properties. We'll see two properties of the process of differentiation. So first is that differentiation of any constant should be 0 if c is a constant. Okay, and this totally makes sense, because if you think of the graph of a constant function, okay, it's a horizontal straight line. So obviously slope is 0. So this is the first important property for us. Abhinav, you got the answer now?
Yes, sir.
Oh, okay. Okay, so this is an obvious property. Okay, now the second property is that if we have differentiation of a constant multiplied by a function, that can be simplified as take the constant outside and differentiate the function. So for example, if y is equal to, let's say, 3x cube, okay, then what will be dy by dx? So we'll just apply this second property now. Dy by dx will be differentiation of 3x cube. Now 3 is a constant, so I'll just take it outside the differentiation operator. And now I'll use the x to the power n rule. So this will become 3 into 3x square. So this will become 9x square. So becoming this. Okay. Or if I have y is equal to, let's say, 4 root x, okay, then dy by dx I want to find out. So just take the 4 outside. We're left with this. This becomes 4 into differentiation of x to the power half. So this becomes 2 by root x this time. So that's what my dy by dx becomes. Okay, and the final thing for today's learning, if we are differentiating the sum or difference of two functions, then that simply, so this is like a commutative property. Oh, sorry, this is like a distributive property. If you open the bracket, it just distributes plus or minus, whichever be the case, like this. So these are very common types of properties which are in other operators also. Like if you see the mod operator, or the distributive will not apply to the mod operator, but the constant one will apply to mod. Or for example, if you see operators like sum, difference, etc., see that they apply these. So here, for example, if we have the function 3x square plus 2x, so rate of change will become differentiation of 3x square plus 2x, which will become differentiation of 3x square plus differentiation of 2x. So here we are applying the distributive property. So we opened this bracket. We opened this bracket here by separately adding the rate of change of the two terms. So this becomes 3 into 2x plus 2. So it becomes 6x plus 2. You can justify this way also. Or you just understand that it's a linear function. Yes.
So like, how do we visualize that second one? Like when constants comes out, and that we like, how do we visualize it graphically?
Instead of graphically, now you go back to the definition of dy by dx, and you'll find it easy enough to justify it. Okay, if y is equal to a constant into a function, then dy by dx is limit delta x tending to 0 of c of x plus delta x minus c of fx divided by delta x. Now you can see from here how it comes. ठीक है ना? Graphically, the visualization is little different, because what we'll have to understand is the relationship between the graph of fx and c times fx. So the graph shape changes. So accordingly, the slope of the tangent at any point changes. For example, if you were to compare the graph of y is equal to x square and the graph of y is equal to 2x square, you will see that they are slightly different parabolas in terms of shape. So it's not that easy to directly justify it. Okay. For each case you can justify. Like if you were to draw the graph of y equal to x square and y equal to 2x square and compare them point by point, then you'll be able to justify this. But algebraically, it's very easy to understand why this happens.
Okay, sir.
This is clear, no? The algebraic one is clear?
Yes, sir. So like you took C out because C is not going to be affected by that limit of delta x, right?
Correct. Yeah. So when we are calculating this change in y upon change in x, C is common here. No? So C just comes out. So it just becomes C into this term. And this term is nothing but rate of change of the function fx. So the rate of change of C into fx just becomes C into rate of change of fx. Okay, people, so hope these examples are clear. So with that, we come to a conclusion for today's lecture. So I hope you have enjoyed the lecture and you found it smooth enough to learn the new formula and a few applications that we've seen today. Also, just go through the solutions, or rather the hints that I've sent you for the worksheet number 1. And if any question is unclear from it, please send it to me. I will help you out with that. Okay, you can send me in WhatsApp, or if you have joined the Discord platform, then in that for your Genius house, you will see that or Genius group, there will be a particular channel for the physics doubts. Okay, so you can post it over there also. So the advantage will be that whatever reply I post, that will be there for future reference for that also. Okay. So that's it for today's session, people. Wish you all the best. Okay. You can
Sir,
send on WhatsApp also doubts. Yeah.
sir, can you please show the proof of that 3x square once again?
Yeah. Just show. Okay, this one.
No, sir, not
Right.
this. Y is equals to x cube, the first example.
Oh, that one. No? Okay.
Yes.
This one.
Yes, sir.
Yeah. Okay. Okay. Just go through it. If you have any doubt, you just let me know. Okay.
Thank you, sir.
Okay. So that's it for today's session, people. You can log out if you're finished.
Thank you, sir.
Thank you,
Okay,
sir.
all the
Bye,
best.
sir.
Thank you, sir.
Bye, people. All the best.
Sir, I wanted to ask you a few things. So like, what would be the proof of that third rule that if we have two functions and we need to differentiate them? Like,
The sum of two functions.
yes, sir.
So try it out yourself. जैसे वो algebraic method से किया ना, वो constant वाले के लिए जैसे किया, just try it out yourself.
Okay, sir.
ना, so you will see delta y by delta x को define करो पहले, और उसमें फिर limit substitute करो that delta x is tending to 0. So it will be quite easy to separate out the two functions.
Okay, sir.
Like change in y upon change in x will become like the change in the first function plus the change in the second function, whole thing divided by delta x.
Also, sir, like that last class you gave us a homework that prove a plus b whole square by another method than those two methods you described in class. So,
Yeah.
so like, sir, like, I couldn't find one. So, like,
Which one?
like, so you said no, that we have to try that. How
Pythagoras theorem.
no, like that a plus b whole square, prove it by a graphic other
Oh,
than
achha,
graphic.
achha, yeah, I remember now. That's a very interesting thing. I'll just give you a hint, and maybe we'll do the full solution in the next class. Okay, it's a very nice geometrical way of proving it. Okay, so it's like this. Okay. So suppose we have this now. Now in this is A and this is B. Okay. So similarly here, this is B. This is A. And if we take the whole thing, then this is L. This is L. So L square is equal to A plus B whole square. Okay. Now it will be equal to the sum of this area, okay, plus this area, plus this area, plus this area. So just see if you can prove it.
Yeah, so like A1, the blue area of A square, and then that smallest square is B square, and then
Yes.
two rectangles are like
So
AB.
if you do this now, if you just prove this now, you will be able to show that it is equal to A square plus B square plus 2AB. So this is a simple geometrical way of proof of.
Okay, sir. And
Yeah.
sir, like one last thing, like anything, what's the homework for today, and like, do we need to solve like our module or read it or anything like that, or HC Verma?
Yeah, I will be giving you the module. I mean the homework in a separate sheet. I'll send it to you, and in that, like as we cover more things, the questions from the module will also be included. Okay, apart from the worksheet questions, in that worksheet itself, I'll mention that which exercise of the module, which questions you can do. Okay.
Okay, so you'll send it on WhatsApp, right?
Yes, and I will send that on WhatsApp. And for reference books like HC Verma and online, just wait a couple of weeks. Okay, we will first send a list of reference books, and then I'll start referring. Of course, HC Verma will be the primary reference book apart from the module. Okay, so you can just wait a couple of weeks. If you are actually like if you can't hold your energy and you want to go ahead with HC Verma, you can do that. That's no problem. But officially, the assignments I'll be giving in a couple of weeks. Okay, from HC Verma.
Okay, sir. So like for now, like this this very moment.
Yes, for now, just the assignment that I send her, that will be what you have to do. And in that assignment, either there will be only questions or questions plus some list of questions from the module. Okay.
Okay, sir.
Okay. Okay then, people. Okay.
And
all the best then, people.
Yes, sir. And
Yeah.
sir, last one thing, like in our
Yeah.
module, there was one question that what is 1 by infinity? So the answer in module was given 0, but it should be tending to 0, right?
It's tending to 0. That's correct. Okay.
Yeah.
Actually, it's actually technical. I'll tell you, it's 0 is correct actually. See, the thing is, if we write 1 by x now in that, if we put x tending to infinity, then 1 by x tends to 0. You understanding?
Yes, sir. Because like,
But
x
if
is
we
not
put
exactly
x,
infinity. It tends to infinity.
So the proper way of describing 1 by infinity is that it is 1 by x where x tends to infinity. So if y is equal to 1 by x, then as x tends to infinity, y tends to 0. And on the other hand, as x tends to 0, y tends to what? Infinity. Okay, so those are two sides of it. So we will be discussing hyperbolic function in detail in the future. So we'll know more about these limits there also. Okay.
Okay, sir.
Okay, people. So that's it for today. Okay. Wish you all the best.
Thank you, sir.